We present a unified spatial-angular structured light for single-view acquisition of shape and reflectance. This is an overview of this video. In order to acquire high-quality geometry and materials, active lighting is indispensable. For example, spatial structure light is widely employed in 3D scanning to obtain a detailed geometry. Light stage setup can capture high-quality appearance of the object in angular domain. However, there is no device can cast both spatial and angular structure light. Directly combining the two types of lights ends up with a bulky setup. To tackle the challenge, we propose a unified structured light for high-quality acquisition of 3D shape and reflectance. Our lightweight acquisition setup consists of a LED array, an LCD mask and a camera. For depth acquisition, each LED can project a set of mask patterns into the space to encode shape information. For reflectance acquisition, a set of light patterns cast through a transparent mask to sample the reflectance. We propose a novel acquisition pipeline for our setup and achieve high-quality results. First, we pre-train 18 mask patterns and 32 light pattern, and then capture the corresponding images. Applying the decoding algorithm to 18 images, we can obtain the depth map and further reconstruct the mesh. With the mesh and the captured images under different light conditions, we perform differentiable rendering optimization to obtain the reflectance results, which are stored as BRDF parameters in texture maps. Finally, we can render the object with novel lighting and view conditions. Highly accurate geometry can be captured with structured light, and various patterns have been studied to improve the accuracy. Recent work Structure Light à la carte presents the first computational approach to optimal design of patterns for structured light, which outperforms state-of-the-art triangulation techniques. But the depth accuracy is limited by the projector resolution, due to its error function is defined on pixels. For reflectance acquisition, a representative work is differentiable acquisition technique, which learns a set of light patterns to reconstruct the reflectance. These works can achieve high-fidelity results on non-planar. However, they assume that each point can be illuminated by all LEDs and the visibility information will be baked into material. This is the detailed configuration information of our setup. In order to obtain high-precision geometry, the accuracy of calibration is crucial. We calibrate each LED separately and consider them as area lights. A lot of corresponding point pairs are used as training dataset to optimize the LED positions and the transformation of mask plane in a differentiable manner. For most structured light methods, each mask pixel corresponds to a code vector, and each image pixel corresponds to an observed vector. The masked pixel with the code vector most closest to the observed vector is the corresponding pixel. The disadvantage is that the accuracy is limited by the mask resolution, making it difficult to determine the position more accurately even if a perfect match is found. Therefore, we convert it to the camera array. Sample candidates along the camera array. Each candidate has a code vector which is encoded by the mask patterns. We no longer look for the correspondence between camera pixels and mask pixels, but rather for the correspondence between camera pixels and candidate points. In the case of an ideal point light, sampling candidates along camera array still cannot improve accuracy. Because the code vector of candidates x1, x2 are the same under a point light, since they physically correspond to the same mask pixel. But for an area light in our setup, the codes could be different as they are different physical mixtures of neighboring mask pixels. It shows that the area light performs convolution operation on the mask pattern and the code could change continuously along the camera array. This idea make it possible to achieve a higher accuracy beyond the low resolution of LCD mask. Next, we present our depth decoding algorithm. We first take M images under M different binary mask patterns. Each pixel corresponds to a camera array. We sample candidates along the camera array and calculate the code vector encoded by the area light and mask patterns. The candidate which has the highest ZNCC score is the best matching point and will be selected as the predicted depth of the pixel. Ideal mask patterns should make the code of candidates as distinguishable from each other as possible. We cast this to a multiclass classification problem. For each camera array, first randomly pick a candidate as ground truth label. Next, simulate the measurements with random albedo and noise and then perform the same match operation like depth decoding. Finally, the cross-entropy loss encourages a higher probability for the labeled class. It's easy to extend our idea to multiple LEDs in the setup. Simply concatenate the codes and measurements, and then perform the same matching process. Our reflectance pipeline consists of 3 steps. First, we pre-train 32 light patterns, next capture the object under these light conditions. Then we discard the decoder and optimize the reflectance based on differentiable rendering. For each image pixel, we can look up its texture coordinate to bilinearly sample the neural texture to obtain a feature vector. Then, 5MLP are responsible for transforming the feature vector to GGX parameters, including normal, tangent, diffuse albedo, specular albedo and roughness. In addition, based on the position and mesh, we can directly obtain the visibility using ray tracing. Finally, the measurements can be calculated based on the rendering equation. We aim to jointly optimize the neural texture and 5MLPs to minimize the per pixel differences between the photographs and the simulations. We pre-train 72 mask patterns for shape acquisition. The acquisition time is about 24 minutes and it takes 8 minutes to compute a depth map of 1500 by 1500. For reflectance acquisition, we pre-train 32 light patterns. The acquisition time is just about 10 seconds and it takes 1 hour to optimize the reflectance stored in the texture maps. These are learned mask patterns, light patterns, and the corresponding photographs. In our experiment, we achieve on an average geometric accuracy of 0.27 mm. Our results outperform gray code and MPS in terms of accuracy and completeness. We compare our reflectance result with the state-of-the-art method. In all cases, our results are of higher quality. In addition, our pipeline is highly flexible. It can automatically adapt to given mask pattern number. Using only 12 mask patterns can produce geometry with reasonable quality. The shape quality improves with the number of mask patterns. This experiment shows that multiple LEDs can further improve the geometric accuracy and completeness. We also study the impact of light patterns on reflectance quality. First, our learned patterns outperform the same number of randomly point lights. We also test different numbers of light patterns. Our current choice of 32 strikes a good balance between reconstruction quality and acquisition speed. Here is a summary of our key contributions, including a lightweight acquisition setup and a differentiable calibration method for LEDs and LCD mask. A novel structured light algorithm for depth estimation with area light and the reflectance fine-tuning algorithm based on differentiable rendering. Finally, our work is also subject to a number of limitations. First, for depth acquisition, a long exposure time must be set due to the drastically reduced radiances after going through the LCD. Next, the current set of multiple LEDs are manually selected and may not be optimal. Third, we don't consider the complex light transport like interreflection in reflection estimation. We believe that our work is only a small step toward structured illumination in the spatial-angular domain, and there are many exciting research possibilities in the future. For example, it's interesting to explore joint multiplexing of both LEDs and mask or establish an adaptive pipeline for the joint capture. What's more, we are intrigued to develop a handheld scanner with light field structured illumination.